Finding the equation for an exponential function. Let's talk about how to find the equation for the graph of an exponential function. So this is actually a pretty complicated looking exponential function. It's not one of our toolkit ones. We know that because it's not above the x-axis. So I'm going to think about how you might obtain this graph via transformations of a basic toolkit exponential function. That means something like y equals 2 to the x, or y equals like 1/2 to the x, or y equals 1/3 to the x, or y equals 3 to the x, and so on. So I can see that there's an asymptote right here, and that's not in our typical spot on the x-axis. So we know that there's been some shift up, down. I can also see that the graph is below this asymptote, and we know that toolkit exponential functions, they have graphs that are above. So I'm going to think about how I've obtained this graph via reflecting the graph of an exponential function over that asymptote. So it must have, before we did some transformations, it must have started up there. Where do I know, or how do I know where to put some exact points? Well, I can see clearly there's a point here and here on my grid. So this one is at 0, -2, and this one over here is at -1, -5. And so what I'm going to do is I'm just going to make sure that this point up here on the green graph is the same distance from the asymptote as this point down here. So I can see that this distance is 3, and I want to make sure that this distance here is also 3. And so to do that, I put my point on the green graph at 0, 4, so that they're both the distance 3 from the asymptote. Using the same logic, we can say, okay, this point at -1, -5 is the distance of 6 from the asymptote here, so I need to go up 1, 2, 3, 4, 5, 6, which puts us at -1, 7 up at the top. Okay, so I'm keeping track of a couple points on the black graph as I imagine how it was moved to, how another graph was moved to get it. Okay, we can also see, okay, most of our graphs, they don't have asymptotes. Our toolkit functions have asymptotes at the x-axis, not shifted up. So we must have gotten this green graph via shifting a basic exponential function up 1 from, usually we have asymptote at the x-axis. So we got this one by taking points and moving them up 1. So if we go backwards, we can think, okay, there was a point at 0, 3 that went up 1 to 0, 4. There was a point at -1, -6 that went up 1 to -1, 7. Okay, now this purplish pink graph here, it actually looks more like something like a basic toolkit exponential function. The only thing that's a little bit weird about it is it has y-intercept 0, 3, and we know that our toolkit exponential functions, they have y-intercept at 0, 1. So how would we have ended up with a y-intercept at 0, 3? Well, we would have multiplied each y value of our toolkit function by 3. So I'm thinking that our original graph, it had y-intercept at 0, 1, like most of them do. So at 0, 1. And how did we end up moving from 0, 1 to 0, 3? We multiplied the y value by 3. So we would have gone from 0, 1 to 0, 3 by doing a multiplication of our y value times 3. So to go backwards, we take the y value of 3 and divide by 3 to get 1. To go backwards for the point -1, -6, I can take the point -1, -6 and divide by 3 to get -1, -2. So this point was probably at -1, -2 before being stretched. Okay. So where do we go? Actually, this was a +6. Sorry about that, you guys. This was -1, +6. So that's actually +2. I caught that because I knew that was at +2 right there. Okay. So here's what we know from everything that we've just done. We know that we have started with a graph of the form y equals b to the x. So we start with an exponential function of that form, where the blue one right here is it. And then what we did is we reflected it over the x-axis and stretched it by 3. So how do you reflect over the x-axis and stretch by 3? What you do is you put a -3 in front. So this is what happens when you reflect and stretch by 3. Then what did we do? Well, we added 1 to shift the graph up 1. So we did +1, and that's shifting up 1. The only thing that we need to figure out at this point is, what is this b here? So like, what is the blue graph that we started out with? So what is b? Well, you can figure out what b is in a couple of ways. One is you can look at the graph here and you can plug in the point -1, 2 to figure out what b must be. And then another way would be to look at the black graph and then plug in a specific number into our transformed equation to figure out what b is. So what I'll do is I'll take the point -1, 2 on the blue graph, which is the one we started with, and I'll plug it in to y equals bx. So what's b? I take y equals bx, and then I know the point -1, 2 is on blue graph. So if I plug -1 into the x spot and 2 into the y spot, I'll be able to solve for what b is. So this tells us that the graph that we started out with is equal to -3, 1/2 x plus 1. So just to reiterate how I went about figuring this out, I took the black graph and I thought about, how would we do transformations of a very basic exponential function of the form, say like 3 to the x or 1/3 to the x, and get this black graph? Well, I know that it would have to have been reflected because our basic ones are above. So I know there's a reflection, which tells me that there's definitely a negative sign here. I know that there's been a shift up 1 because this asymptote is up here at 1, and that's where this +1 comes from. I know that there's a stretch by 3. I know there's a stretch by 3 because of how I have this point at 0,3 here instead of 0,1 on the y-axis. So when I backtracked, I found that I have this graph that has y-intercept 0,3, not 0,1, and that tells me what the stretch is 3. Then I plugged in a point to figure out what b had to be. So I ended up plugging in a point to figure out what b needs to be. So this is one way to do a problem like this.